Thank you, Lance. It's a pleasure to be here today, and I'm really excited to speak with you about some of my experience applying graph algorithms within cybersecurity. My name is Elizabeth Maida, and I'm the founder and CEO of Uplevel, a cybersecurity company applying graph theory and machine learning to enhance the effectiveness and efficiency of security operations teams. Now, the title of my presentation is A Picture is Worth a Thousand Rows. And in many ways, this really encapsulates one of the core advantages that graphs can provide in cybersecurity. Many times, security analysts are stuck reviewing thousands of rows like the ones you see here, and are trying to make the connections between those rows entirely based on their own experience. So I'm going to share some background on how graph algorithms can help automate that process. Now, I think people tend to believe that security is a very technically sophisticated domain. So I wanted to share a little bit of background on the reality. Similar to a lot of other industries, there is an overabundance of data. The average large enterprise usually has over 40 security vendors across the network and endpoint devices. And those vendors are generating over 1,000 alerts per week. To further compound this data problem, the organizations are also receiving millions of pieces of threat intelligence or rules about what should be considered malicious. So ultimately, in the average large enterprise, more than 90% of this security data is thrown away. The top questions that security teams are dealing with are around: how does this alert relate to anything we've seen in the past? And is this actually an indication of malicious activity? But due to resource constraints, it's impossible for them to investigate everything. Organizations are still largely dependent on humans spending 16 plus hours investigating an alert and coming to some conclusion about whether it's actually malicious activity. So you may be wondering what they're doing during this time. An analyst will copy and paste values from an alert to create a series of searches using the results from a previous search to inform the next search. Usually they're searching through something like Splunk. There's an example of Splunk right here on this slide, but it could also be a data lake or a database. With security, they're typically looking at what's called a SIM, a security information and event management systems, but you can really think of it as a large collection of logs. Security analysts will then also check random websites, search through emails, compare their results against spreadsheets, ultimately enriching the information that exists in the SIM with this open source data. And in some cases, the analysts may actually write down the results on paper, almost creating their own directed graph based on their search history. So oftentimes, because this is such a manual time-consuming effort, organizations will create and save frequently used searches in advance. So these searches are often designed to flag suspicious activity. So for example, an unusual number of requests from the same IP within a limited time frame. In order to write these searches, you really need to have an idea of what you're looking for. So teams will often meet on a weekly basis to identify the activity they would consider to be malicious. They'll confirm the data actually exists in the log store and then write these correlation searches, essentially creating rules-based heuristics. When something matches these conditions, it triggers an alert similar to the other alerts, but based on more complicated logic. Some of these rules are written by the security team within the organization itself, and some are actually pre-packaged and provided by the vendor who develops the SIM. So you end up with hundreds of rules from different creators, which can create a huge maintenance burden. It's a really time-consuming manual effort to create and analyze the effectiveness of the rules, especially if you weren't the one who originally authored them. There's also a lot of complexity as you end up with many potentially overlapping rules with different priorities. And so trying to sort through which rule actually applies in a certain circumstance is an incredibly challenging endeavor. So even after you go through all of that effort of creating and managing these correlation searches, you still really end up with a dashboard like the one you see here. And the security analyst has to pick something to investigate based on general instinct about what looks particularly malicious. So there are still just these inherent limitations on how you determine if these different roles are actually related. And so while some roles may have been combined as a result of correlation search, it's only because you really already knew that the underlying activity indicated malicious behavior. So graphs can help with insecurity not just in terms of visualizing the data, but also analyzing the underlying data. So, with the graph representation, an analyst can immediately see the clusters of correlated alerts, like in the example we have here on the screen, that should ultimately be investigated as a single unit or that may be related to significant past events. And behind the scenes, graph algorithms such as community detection can effectively replace the need to be writing and managing hundreds of correlation rules. Now, there are multiple situations that might actually result in having all of these disparate pieces of information about the same attack that would warrant and require the use of graph algorithms. So, for example, you might have alerts about the underlying event coming from multiple different devices. A great example of this is that even just on your laptop, you may have antivirus software, Microsoft Defender, and endpoint detection and response all running at the same time. So if something bad is happening on your laptop, all of those different pieces of software might actually flag it. You might also have situations where there are sequential events that are all related to an ongoing attack. And a denial of service is a fairly straightforward example, as it's really the same activity that's occurring, but it's being repeated over an extended period of time. You may have multiple alerts, flagging the exact same tactic by the same, threat actor. A phishing email campaign is a very common example of this, where you have multiple versions of a very similar email but sent to different recipients. And finally, you may have a variety of alerts that actually constitute a progressing attack or attack vector. And so that could be the case where you might see a phishing email that's followed by some registry edits and then some unusual outbound traffic. And in that case, you actually have a lot of the evidence in your log data store. The challenge is figuring out which pieces of data are actually related and constitute that attack vector. Now, before we get into more detail about how the graph algorithms can be applied, I wanted to quickly provide a highlight of the data that we're actually dealing with and introduce some terminology. So an alert, which I've referenced multiple times, is really what you see on the right-hand side of this slide. You can think of it as an event that's triggered by a security product, so something that might be on a laptop or the network firewall. And that event is really triggered because there was some type of activity that actually matched one of the predefined rules defining bad behavior. Now, within these alerts, as you can see here, there's a lot of individual technical attributes or characteristics. And this is what we generally refer to as an attribute. It's these individual fields, such as the file hash is an actual attribute of a file. And then the final term that I thought it would be useful to highlight is indicator. An indicator is a piece of intelligence indicating that a specific attribute or group of attributes identifies malicious behavior. Now, I've done a previous presentation at NEO's Nodes conference that goes into a lot more detail on how we thought about the data model around all of these data elements. So I would definitely recommend referring to that for more detail. But this should hopefully provide a high-level overview of the type of data that we're looking at. So as a starting point, community detection algorithms are really useful to help identify related alerts. The definition of community detection algorithms are really focused around identifying related sets or clusters of nodes that are naturally occurring within the graph. So essentially a set of nodes that are more closely connected to each other than to the rest of the graph. And so in the cybersecurity case, a cluster of nodes is a set of related alerts that should be investigated as a single unit, as they're likely to all be pieces of evidence in the same or related attacks. There's multiple different types of community detection algorithms, clustering coefficients, connected components, label propagation. And there's actually a really great resource that I mentioned on this slide, the Graph Algorithms book, Practical Examples in Apache Spark and Neo4j, that provide a lot more details both on the definition of the community detection algorithms and also sample implementations. Now, in our case, a lot of our work was focused on connected components, really finding those groups of related alerts. And on the right-hand side of this slide, you can see some sample queries using Neo's Union Find algorithm that helped us identify the connected components. We also then built upon the union find and the results of the union find algorithm to start getting a list of the actual components or partitions that were a result of that algorithm so that we could get an idea of the number of partitions, the size and density of those partitions. In our case, the relevance of the number of nodes in each partition versus the number of alerts were really helpful areas for us to guide the investigation for the security analysts. Essentially, you're breaking this larger graph into smaller subgraphs and then identifying which subgraphs are worth further investigation. So, one thing that we definitely found with cybersecurity teams is that it was actually really helpful for them to look at both the visual representation and then also the written details of the alerts and attributes within the cluster. So, as you can see here, we would really pair that visual representation of the individual clusters with those written details and allow people to navigate through both from the visual side and the written side to see what information actually constituted the various specific clusters. Ultimately, if an analyst determined that a particular cluster really did warrant further investigation, they could then send all of that detail of the associated events to a JIRA or a ServiceNow and officially start an investigation. Now, I want to go into a little bit more detail on our clustering approach, as it's not quite as straightforward as simply identifying groups that are all connected within the graph. We actually introduced some enhancements by pre-processing the graph prior to applying community detection algorithms. And I think this is a very common approach that you see in terms of applying such algorithms. So in our case, there were exact attribute matches that you can see when looking at the graph. But there were also some heuristic attribute matches that we introduced, which are really specific to the security data. And this is a great example of domain knowledge about the data itself in the graph can really allow you to optimize how you apply the algorithms. So in our case, we thought of these as equivalence detection modules, and they're really specific to each attribute type. So for example, we would check for shared subnets between IP addresses or shared prefixes for file paths. We also have more advanced modules using text similarity algorithms like edit distance, longest common substring analysis, applying NLP techniques such as named entity extraction for email bodies. You get the idea. It was really based upon the different attribute type. There were different techniques that provided enhanced knowledge. So in this example, if you look on the left-hand side here, we're highlighting two nodes that are each representing an attribute, different file names, but they're not actually the exact same node because the file names are slightly different. They just happen to match a general pattern that we identified based upon our text analysis. So we can then enhance the scoring of these equivalent attributes based on temporal dynamics, event categories, and the role of the attributes within the events. So you can really think of this as scoring the relationships between certain nodes. So even though everything might appear connected visually, our clustering algorithms might identify a subset of a visually connected component as something that's actually related. And you can see just an example of this on the right-hand side. Only a subset of that overall cluster has been identified as a set of related alerts related to malware activity. And it's because there was this pre-processing and really domain-specific knowledge enhancement of the graph that occurred prior to then applying the community detection algorithms. We then also use another class of algorithms, centrality algorithms, to help prioritize these alert clusters. Because again, you first do this automated clustering to find the related alerts within the graph, but then it becomes a question of, just because something is a partition subset of the overall graph doesn't necessarily mean that it requires and warrants an investigation. So centrality algorithms really focus on the number and nature of connections. And they're very much related to just the fundamental graph topology. So these can include degree, the number of connections, betweenness, nodes that have the most control over the flow between different nodes and groups, and PageRank, which node is, the most important within a particular group. So in order to prioritize the clusters and help guide the security team in terms of which events to focus on, We will use parameters on individual nodes as well as apply centrality algorithms to determine the importance of distinct nodes within the cluster. And just as some examples, if a cluster contains alerts or information from a highly trusted source, where highly trusted might be that they have a very good reputation in terms of having minimal false positives, the cluster could be assigned a higher priority because it's considered far more likely to truly be a significant event. However, there might be other information indicating that when certain alerts are combined with other data, they're actually indicative of benign activity. And so that cluster is actually deprioritized accordingly. So these were just a few examples of how community detection and centrality algorithms can help identify and prioritize related alerts. One of the really exciting things is that a byproduct of this analysis, so specifically some of the text pre-processing, can actually also help dynamically generate new intelligence that can be used to proactively identify attacks. So I know I had mentioned indicators earlier in the presentation. Those are the technical characteristics which have been flagged as being indicative of malicious activity. There are a lot of reports that are publicly available that talk in a lot more detail about threat actors and the known indicators that are indicative of their presence or their involvement in an attack. And I have here on this slide a recent example from a recently published report from FireEye, which covers APT 41, so Advanced Persistent Threat 41. APT 41 is a threat actor involved in both state-sponsored activity and its own cybercrime operations, which target a variety of industries, everything from healthcare, high-tech media to retail and telecom. And so, I highly recommend taking a look at the FireEye report or other reports to get an idea of the level of research and effort that goes into uncovering the tactics, techniques, and procedures and indicators associated with these threat actor groups. And so you can see on this slide, there's some examples of the types of indicators that you might get, the file hashes and the domains that are presented there. And those file hashes and domains and related indicators can be used either in the security products themselves to generate alerts or in the SIM correlation searches that we talked about earlier. But the challenge is these indicators are always shifting. And the graph analysis, specifically the combination of similarity analysis and community detection to identify related alerts, can also help uncover these potential indicator patterns. Many of those indicators that are the output of the graph analysis can actually be broader than the indicators listed here because the graph analysis can help generalize multiple indicators into regular expression patterns, as an example. Another advantage of doing this automated analysis is that the indicators can thereby be updated far more dynamically and capture the very latest information without having to involve huge research teams of people. And this is not to say that you would want to do all of your indicator analysis in an automated manner, but it can really help augment and enhance the work that an independent threat research team might be doing. So, we've focused a lot on community detection and centrality algorithms and a bit about how text similarity analysis can contribute and enhance both of those. There's a number of other opportunities, though, for graph analysis and graph algorithms within cybersecurity. One of the main ones is actually around creating attack pattern fingerprints so that you can then look for essentially these subgraph patterns within a larger graph and apply things and look for subgraph isomorphism, where you're really looking for the pattern of nodes and relationships and labels and properties and potentially directionality and trying to find those patterns elsewhere in the graph. You can also apply label propagation to cascade maliciousness throughout the graph. So if something is malicious and is closely connected to another attribute, that often increases the likelihood that that attribute is malicious. Similar to community detection, you definitely want to introduce enhancements so it's not quite as straightforward as just assuming that everything that is connected is also malicious. There's also some related works around statistical relational learning where you use the graph topology to actually predict and provide a level of confidence of what the label should be on related nodes. And then finally, you can also use centrality algorithms to analyze the tactics, techniques, and procedures across different attackers or threat actor groups. So you can identify the most common techniques or the ones that are most indicative of sophisticated targeted activity and potentially find related threat actor groups as a result. And again, that can be incredibly valuable, especially for the teams that are focused on the threat intelligence research work. So thank you very much for joining this presentation today. Hopefully this provided some context about the potential value and applications of graph algorithms in cybersecurity. I think we have a few minutes now for questions, so I'd love to answer any questions that people might have at this time.
Yeah, all right, great. Thank you so much for that, Liz. That was really great. That was a really interesting presentation. Our audience members, if you have any questions, you can go ahead and type those into the Q&A portion of your Big Marker control panel. Looks like we already have a couple coming in, so I'll go ahead and get to those. But so how do you quantify the value of using graph algorithms within cybersecurity?
Yeah, so it very much depends upon the use case and the intended use of the graph algorithms. When we look at our primary use case, for example, around community detection and looking for correlated clusters of alerts, a lot of the metrics that our teams will use is the number of alerts that need to be investigated. So we've often seen situations where they'll see that the number of alerts requiring investigation is reduced by 80%. They'll also look at things like mean time to resolution, because one of the other advantages of the graph analysis is that it's really providing the analysts with much more context at the beginning of the investigation. So rather than spending their time going through and running all these searches, they have a lot more information that they can start with at the beginning of it. The other thing that we have seen, and this speaks to kind of the correlation searches comments towards the beginning of the presentation, is that oftentimes it's a pretty huge people investment in terms of people understanding what rules have actually been created, how they interact, maintaining and updating those rules. Like, you almost need to either become a specialist or bring in external consultants. So being able to kind of reduce the operational overhead in that way, and the actual technical debt that may be incurred from years and years of rules, has also been one thing that people have really looked at in terms of the value of using graph algorithms in this circumstance.
Interesting. Okay. And do you run these algorithms over the entire graph, or what are the performance implications?
Yeah. Well, so I can speak specifically to our experience, because I think oftentimes it really depends on the nature of the graph. In our case, a lot of the community detection we will run at regular intervals and almost in offline manner, so kind of like a batch processing of the graph, and do far more localized real-time processing. We'll also store the actual partition IDs as labels on the nodes themselves, and then do this ongoing almost performance analysis to identify how often those partitions change. So in our case, usually the situation in which the partitions change is with the addition of a new piece of data that brings two existing clusters together. Otherwise, it's really more of like additions to existing partitions or the creation of new ones. So in our case, we see a lot of natural partitioning in the graph, so we don't need to really be analyzing the entire graph at one time. We can do any of the full graph analysis in much more of this kind of offline batch mode, and then have very localized analysis that is occurring much closer to real time. The other thing that I would note is one of the ways we were able to create the graph, so it wasn't, just one gigantic, very dense graph, is just making sure that our data model accounted for things like supernodes. So for example, we don't have a node in our graph that's like gmail.com, as that would connect 80%, I would say, of the graph together. But by excluding that, it really allows us to do a nice combination of this batch analysis with something much closer to real time on a localized area.
Yeah, sure. And I think, okay, our final question here, how might these techniques apply in other industries?
Yeah, it's really interesting, because I have definitely seen that there's some very common themes that are faced by operations teams in a whole variety of industries. Well, really, operations teams are in a position where they're, reviewing huge amounts of logs to identify potential errors. And this can be everything from life sciences to retail to folks that are just managing big, software development platforms. And so they'll be using, something very similar to the SIM, if not an actual, SIM, but really the log type infrastructure, Splunk and Elastic are two prime examples. And in almost all of those cases, it's this challenge of trying to figure out what queries need to be written and understand how the data within these log processing systems is actually connected, and how they actually encode all of the business logic about what should be something that they're paying attention to into these complex rules, where all of a sudden the rules pile up and you don't actually know how they interact. So I think there's a lot of opportunity in these cases where you find yourselves kind of continually having to search through the data and writing queries, actually thinking instead about, can you actually encode some domain knowledge just in the underlying data model, and then applying different algorithms based upon the business question and the use case that you're trying to solve for.
So interesting. Thank you so much, Liz. Marilee, I'll pass it back over to you.
Great. Thanks so much, Greta. And Liz, thank you so much for spending time with us today. It's always such a pleasure having you with us. So I really appreciate your time. Thank you. And Greta, thanks for hopping in and doing Q&A. That was awesome. For those in our audience, just to let you know, our next session featuring our guests from Deloitte will be starting in just a few minutes. So we'll see you in that next session. Thanks so much.